Hey, what you're looking at here is problems number 23 through 32 from the mole worksheet number 8. This is just random problems on the mole, meaning stoichiometry problems. And if you've come to this site, I think this is good practice. We could be asking you anything about the mole. These tend to be close to college level problems here, so some can be a little bit challenging. I'll be doing each one. Well, technically I'll be doing every other one. Notice that every other one is solved. You'll have to do the even ones, but you can use the odd ones as a guide. Also, the answers are given, so you just have to show the work to get there. If you need to, for example, you just want to know 32, obviously just go ahead and go right to it because there's quite a bit here. Here we go. Number 23, we got 16.4 grams of oxygen. We're reacting it with excess hydrogen. How much water is produced? Okay, nice place to start. I'd recognize this as a gram to gram problem. I'd start with what I'm given, the 16.4 grams of oxygen. By recognizing that it's 3 steps for gram to gram problems, I'd draw 3 lines. I would then write equals blank grams of H2O to make sure I'm heading towards H2O. And then I would go, it's always the same thing, from grams of A to moles of A, from moles of A to moles of B, from moles of B to grams of B. Write that down if you want to have a generic setup here. Doing that, we find that 32 grams is a mole, so we have about a half a mole. But every mole of O2 requires 2 moles, well, I should say can produce up to 2 moles of water. See the 2 in front of it? And what's it weigh? 18 grams. We have enough oxygen to make 18.12 grams of hydrogen. We have excess water, I should say, and we have excess hydrogen, so we're good to go. For you, this is a mole. Oh, it's a limiting reactant problem in dealing with moles to moles. Maybe you can just by inspection figure out the limiting reactant in terms of moles, and then go from moles of your limiting reactant to moles of product. Interesting, it says the answer is 45 grams of NH3. I know that's wrong because that's not moles, so ignore that, I imagine, or see if that's the correct number in terms of moles. I think I went a little too far there. Number 25, sodium metal and water react to form sodium hydroxide and hydrogen gas. How much sodium in terms of grams will react with excess water to make 15 grams of sodium hydroxide? This, I believe, is another 3-step gram-to-gram problem. We want to make grams. We're starting with grams. Start by writing the balanced chemical equation. It's done for you. Start with what you're given, the 15 grams of sodium hydroxide, and find out how many grams of sodium you needed. Set up your equation. It's a 3-step, so draw your 3 lines. Draw equals blank grams of sodiums to make sure you're heading towards sodium. And then convert from grams of sodium hydroxide to moles. Go through mole land here because every mole of sodium hydroxide, as it turns out, requires 2 moles of sodium. You could cross those out and put a 1-to-1 there. And 23 grams is a mole, meaning we better start with 8.6 grams of sodium. It's a match. Nice job. For you, what mass of oxygen will react with 2.64 grams of magnesium? Same thing. 3-step gram to gram should be no problem. 27. What mass of carbon dioxide can be made by reacting 1.56 grams of sodium carbonate with 0.687 grams of hydrochloric acid? Now I can see by the way I did it that I did it the brute force method, meaning I just took each one of those, crunched it through to see how many grams of CO2 it can make, and I circled the lower number. But maybe you could have more quickly said to yourself that, well, let's see, 84 grams, I believe, is sodium bicarbonate. Requires 36 grams of HCl. Do I have twice as much, roughly, grams of NaHCO3? I do, and it's kind of close, so I think I assume that the limiting reactant is HCl, but it's kind of close, so I would check it through. And maybe it's not, because take a look at that. But let's do it. We have enough sodium bicarbonate to make 1.74 grams of carbon dioxide, but we only have enough HCl to make 0.828 grams here. Interesting. It doesn't look right to me, but I'll assume it is. We'll keep rolling. and that's 0.828 grams of CO2. If one of the students notices something's off with this, and I thought they would have been closer based on my calculation, let me know. I got 0.828 grams of CO2. My guess is there might be something slightly off on the top one, but let's assume everything is fine, and there you go. Okay, number 28, you'll have to do on your own. Number 29, a mass of 8.15 grams of ethylene, C2H4, reacts with some extra oxygen if 16.2 grams of CO2 is collected. What's the yield? Well, first we'll find out the theoretical yield. So we'll go from grams of ethylene to grams of CO2. That's a three-stepper, and then we'll see how we did. Crunching it through, as we've done through all the other ones, we see that we have enough ethylene to make 25.6 grams of CO2, but they only got 16.2 grams. Not bad. 16.2 out of a possible 25.6 is 63%. Number 30. Ooh, same kind of problem, so you use it, model it after that. And number 31. Hydrogen and nitrogen gases are reacted to produce a whole bunch of ammonia. That's a lot of ammonia. If the percent yield is only 15.2%, how much hydrogen was initially present? Assume hydrogen's the limiting reactant. Yes, I see that. Okay. Well, what we'll do is we'll find out what the theoretical amount was. The amount, if the percent yield of the reaction was 15.2%, how much hydrogen was initially present? Why don't we find out how much hydrogen is present in theory, and then we'll scale it up to the 15.2%, right? So there's our 2.1 times 10 to the 6 grams of ammonia, right? In other words, there's 1,000 grams in a kilogram, so aren't I cute? That should be an exponent there. But on the fly, I switched to grams of ammonia, and I divided it by 0.152 to account for the 15.2% yield. In other words, we need about 8 times this, 7 or 8 times, because the yield was lousy. And let's go from there to how many grams of hydrogen you must have started with. You could have also just done it just theoretically and then adjust for the 15.2% yield. All right, so 17 grams is a mole. Every mole, 2 moles of ammonia requires 3 moles of hydrogen, which weighs 2.016 grams. So 2.46, that's a superscript, times 10 to the 6th grams of hydrogen must have been used initially. This one's challenging because the adjusting for the 15.2% is not something people do commonly. Number 32 is for you. The answer is given, but you do have to show the work to get there. Good luck with that. This is worksheet 9.8, questions number 23 through 32.